standing. If there's also an overflow space up by the dinosaur, there's a big flat screen up there, so that if you decide to do that, that's up to you. But right now, this is definitely worth standing. It's a great pleasure to introduce Ralph Cicerone for the 2011 Taplin Environmental Lecture, Climate Change, A Scientist's Perspective. Ralph is one of my heroes. He's undoubtedly one of the heroes for many of you. His vita starts at MIT in Illinois in the 60s for his education. Went to Michigan and Scripps in the 70s, where he was a junior scientist. It went to NCAR in the 1980s, where he started out as a senior scientist and ended up a division director, Division of Atmospheric Chemistry. It then went to UCal Irvine in the 90s, where he started out as a professor, went through about every other job above that, and ended up as chancellor of the whole shebang. And since 2005, he has been the president of the National Academy of Sciences and the chair of the National Research Council. He's received most or all of the dominant awards from the American Geophysical Union. This, to me, as a scientist, is always the sign of the credentials that the scientist most covets, or awards from his peers for his scientific work, which was dominated by work on trace greenhouse gases, mostly methane, N2O, methyl halides, and their effect on radiative forcing and climate change. He's received also internationally recognized awards that are given across all of the sciences, including an Albert Einstein World Science Award. He's received honorary degrees from prestigious places, election to, I think, all domestic and many foreign academies. In my view, there is no greater issue today, more at the intersection of science and politics than climate change. If you are here because you're confused about this subject, and especially its recent developments, then I only have two things to say to you. One, join the club, and two, you've come to the right place. At no time in my life, certainly, have non-scientific claims about the veracity of scientific information gained more traction in Washington, D.C. than they do today. But in the end, I believe that it is the scientific information that will be decisive, even if, as I now think is likely, it will take generational change. PEI, Princeton Environmental Institute, is dedicated to the task of arming the next generation's leaders with the sound scientific information they're going to need. And so it is my great pleasure to turn the floor over to Ralph.
Thank you, Steve. I think the last time I was in this room, it was with Meg Ryan, but maybe it was with my daughter. I don't remember. It's really great to be here with so many friends and colleagues over the years. Peter and Rosemary saved me from being lost here earlier today. Thank you. One of my freshman chemistry lab partners is here. I see a truth squad from University of Minnesota and from Harvard here, just in case I make any mistakes. But seriously, it's an honor to present a Taplin lecture. I read a little bit about Mr. Taplin and what a great contributor he was to the Princeton community, and to visit the Princeton Environmental Institute. So thank you, Steve, for the invitation. This topic is one that I think if each of you were presenting a lecture like this, it would come out somewhat differently from the rest, because there's so many facets and aspects to it. There is, of course, the scientific side. There are many, many human concerns, such as population and resources, agriculture, water, implications for energy and how we use it, all kinds of threats and disruptions, and perhaps some benefits that we haven't yet learned about. The title I chose, A Scientist's Perspective, is just that. It's the perspective of one scientist. And I want to emphasize some of what we're learning, and then some of the current challenges as well. First of all, what's happening? I want to provide a quick review of what we're seeing with measurements. Is there an explanation? Is it the only explanation? What can be predicted? This, of course, is the biggest challenge of all. And the point I'll make towards the end. Yes, Steve?
Turns out they can't hear in the back. We're going to have to adjust the sound.
What'd you say? And in any area of science that has implications that are rather immediate and close for various human enterprises, economic or anything else, the science is done in a fishbowl, and the demands on it are actually quite high. In my younger years, when I was worried about whether to work on any kind of applied science, I thought it was messy and dirty and somehow wasn't of the highest standards, and I found out the opposite in my view. So let me go on. Here's an outline of what I'm going to cover very quickly, with quite a few slides. First of all, Earth's energy balance. From a very rough but physically fundamental point of view, how hot should the Earth be and what controls it? Then, of course, the greenhouse effect, a brief review. Then I'll talk mostly about observed changes in temperatures of air and water, sea level rise, and ice losses as measured from Greenland and Antarctica. And then, of course, the inevitable connection with current and future fossil fuel usage. So we start, however, with the perspective that over Earth's history, there is much, much evidence that our climate has changed many times. Sometimes very large-scale changes over large regions, sometimes smaller regional changes, geographically more limited. And then, of course, there are many aspects to climate: sea level, ice amounts, windiness, rain amounts. So these previous changes, in the absence of human activity, lead you to ask, well, what forces do control climate, and how do the human-induced forces compare to them, and so forth. So how is it that humans can affect our planet's climate? Well, there's all kinds of geological evidence, and I'm going to show 3 or 4 quick slides of rough mapping of the ice cover over this part of North America. These are from, there's all kinds of previous mappings from geological inferences like glacier debris, channels of glaciers, rocks, and in the case of fairly recent, that is less than 40,000 years ago changes, carbon-14 dating of residual material. So something like 18,000 years ago, we had very thick ice extending well down into North America, and I'm just going to show very briefly that 10,000 years, 8,000 years, and so forth, the ice was receding. There have been several ice ages, roughly 100,000 years apart over the last 500,000 years, and inferences of warmer climates in the very, very distant past, tens of millions and hundreds of millions of years ago. Inferences that are probably pretty good, but nowhere near as refined, and not the kind of direct evidence, I think, for the most part. Okay, so let me go to Earth's energy budget. This is obviously a cartoon. It's something I adopted and then adapted from the cover of a Physics Today magazine 20-some years ago from our colleague Ramanathan, and I've changed some of the numbers to reflect increasing certainty in some of these numbers, but to a first approximation, we receive about 340 watts, 341 watts per square meter from the sun, averaged over day and night at the top of the Earth's atmosphere. But about 30% of that number, 102 watts per square meter, is reflected immediately back out to space by white surfaces, whether it's light-colored clothing or whether it's snow and ice or whether it's that kind of reflectance from water bodies at the right angles and so forth. So we know that the Earth is not heating up overnight or not cooling up overnight very much. So to a first approximation, there's a balance between the outgoing energy escaping the planet and the incoming. So the incoming absorption is 341 minus 102 on an annual day-night average, 239 watts per square meter being absorbed by the Earth, atmosphere, ocean system. And this is almost all in the form of visible light. The energy spectrum of the sun, although there is certainly X-ray, ultraviolet emission, near-infrared, and so forth, most of this energy is in the form of visible light. The outgoing radiation from the planet is in the form of infrared black body radiation, essentially, because we know what the surface temperature of the Earth is, and we know what its wavelength spectrum of the planetary radiation is. It's measured well. And radiating to cold space, the Earth is warmer than the space surrounding it, so the Earth radiates planetary infrared radiation out, and those two numbers are in rough balance. Now, what's actually emitted from the warmer surface is much larger, and it's a fairly complicated radiative transfer problem to calculate the emission and reabsorption of the infrared planetary radiation on its way back out to space. So the surface emits more, about 239 escapes to space, and I'll explain this just a little bit further. So to a first approximation, this is the control of the Earth's climate. It's energy in and energy out, and the temperature that's established balancing those two energy flows. Well, an indication that there is a natural greenhouse effect was identified about 40 years ago. That, Jerry, you may remember this. Other people did this calculation a long time ago, but with numbers that were not so accurate. You can calculate the temperature of the Earth or any other planet by taking, we know the incoming sunlight as multiplied by 1 minus the reflectivity. This is at a planetary scale now. And a lot of the things in this business are pretty well determined at a large geographical scale, averaging over a long enough period of time. When you get down to details, like the state of New Jersey, it's much more complicated. But on a planetary scale, the energy in is equal to the sunlight multiplied by 1 minus the reflectivity, and you can set that equal to the radiation given off by a black body, the Stefan Boltzmann law. You measure this, you measure that. This is a known constant. You can calculate the effective temperature of the Earth, and when you do it, you calculate that the Earth is frozen solid everywhere. Minus 18 degrees C, or, minus 32 Fahrenheit. Well, what's missing is the greenhouse effect and the presence of clouds. For Mars, if you do the same calculation, you get the right answer. Do we know that Mars orbit around the sun any better than Earth? No. What makes this calculation work for Mars is that Mars has a very thin atmosphere, low pressure, a little bit of carbon dioxide, but not much. So it's as if it's a rock. The atmosphere doesn't influence very much the outgoing radiation. I'm reminded of some of Dr. Manabe's earlier work with radiative balance when all of these things were being mapped out. So for Mars, we get about the right answer, depending on day or night. For Venus, the calculation is grossly wrong. The Venus atmosphere is quite thick, very, very high pressure, largely carbon dioxide, and a number of other polyatomic molecules that absorb in the wavelength region of the outgoing planetary radiation. So this is, in a way, evidence of the presence of greenhouse gases and their ability to control the surface temperature of the planet. Now, in fact, this T sub E, I meant that to be an effective temperature. There is an altitude above Earth's surface, a few kilometers above, where the temperature is minus 18 C. It's above a significant part of the atmosphere, and it's as if the planet is radiating its infrared energy out to space at that altitude. And this is what we've learned. As the greenhouse effect grows, the altitude at which the temperature is at is going to go up also. That's a little bit more complicated, but you got the picture. This is evidence of the greenhouse effect. Now, one of the earliest satellites that orbited the Earth back in the early 70s actually looked down on the Earth. These are long wavelengths, these are shorter infrared wavelengths. And if the Earth were radiating as a perfect black body at 27 centigrade or 300 Kelvin, this curve dashed curve is what the Earth would have looked like. Instead, looking down on the tropical Pacific Ocean, where the temperature is indeed about nearly 300, a little bit less. The actual measurement was this more jagged curve, showing the presence of the absorption bands of, in this case, the pressure-broadened 9.6 micron band of ozone, some CO2 features, and so forth. So what the satellite was seeing, in a way, is evidence of the strength of the greenhouse effect of these gases. And of course, you don't need the satellite to tell you that. You can take these gases into a laboratory, measure their spectra line by line if you wish, although it's not necessary due to the pressure broadening in the atmosphere. Band absorption is usually good enough. So again, this was evidence of the presence of the natural greenhouse effect. Well, just to give you a feeling of the potency here, if you take all human energy usage, where am I? Up here. Take all human energy usage, all coal burning, natural gas burning, all nuclear power, hydroelectric, biomass burning, natural gas, wind, geothermal, and say, let's spread it out over the surface of the planet. What is the power loss, or the rate at which we're using energy for the whole planet? It's 0.025 watts per square meter. I've already said that the energy coming in from the sun is about 10,000 times that number, 239 watts per square meter. The extra heat now absorbed, trapped by the greenhouse gases as of about 5 years ago, was 2.6 watts per square meter, or about 100 times larger than all the energy consumption by humans right now. So if you were trying to change the climate of the planet, for example, to warm it up, burning more fuel isn't going to get you there. You would have to increase it 100 times to get to the same level of the extra heat being trapped by greenhouse gases. So just to give you a feeling of how large this perturbation is, and it's growing. Well, okay, why the concern? Many of you have seen graphs like this. This is now nearly a 50-year record from Dave Keeling, who started out as an organic analytical chemist, but became an oceanographer later, and his son, Ralph Keeling, with significant contributions from other people here and there. On this graph is on this chart are black dots representing the monthly averages of carbon dioxide amounts in air measured on the slopes of Mauna Loa, and then the red curve is Antarctica. And so these are monthly averages of measurements done about once an hour, and there are now many graphs like this from around the world, people using different techniques in different places. When the measurement record started in the late 1950s, 57, 58, there were 312 parts per million. This is now in the dry mole fraction in air. And the number is now about 390. And it's a great deal of science can be learned by studying these wiggles. In the northern hemisphere, or the southern hemisphere for that matter, the carbon dioxide goes up in the autumn and winter, not only with fuel burning, but with the excess of respiration and decay of annual plant material and root respiration, compared to the spring and summer, where the carbon dioxide is on net drawn down from the air by photosynthesis. So in the northern hemisphere, where there's more land, you see a much stronger annual cycle, up and down, up and down, up and down, where Antarctica, although Antarctica is influenced by, for example, our fossil fuel emissions in the north, there's very little annual cycle because there's not much biological activity, or at least photosynthetic activity in decaying organic matter nearby. The most important message for today, though, is the trend. You'll see in a minute that even this number of 312 parts per million is elevated over what the unperturbed natural background would have been. And the rate of increase itself is rising a little bit as our use of fossil fuel increases. So because carbon dioxide absorbs outgoing planetary radiation in this wavelength spectrum, which is otherwise a window region where the air is rather transparent for infrared absorption, carbon dioxide is an important greenhouse gas. There are many, many other greenhouse gases. This is a partial record of nitrous oxide, concentrations measured similarly, only with different techniques, at 5 sites around the world. And the record goes back a few earlier years. This increase is not so well understood. There are definitely multiple things going on, including a few years when there was a significant contribution to nitrous oxide increase due to nylon production, using one of the earliest methods for producing nylon from adipic acid. That emission source has now been brought into check by the major nylon producing companies who are using different processes now. But there's a variety of sources that are causing this, but it's probably most closely due to the use of synthetic nitrogen fertilizers. And in the exhaust end of the nitrogen cycle, N2O is produced, both in soils and in waters. So there are many greenhouse gases. Now I want to show you one of the most important data sets that's emerged in the last 25 years. It's a composite set of data from French, Danish, Russian, and American scientists. I may be forgetting somebody who, and Michael Bender's still here, he knows the story better than anybody, where ice cores have been extracted out of particularly deep and stable ice formations, both on Greenland and Antarctica. Typically, a cylinder can be pulled out and then examined carefully, a very, very long cylinder, and age dated according to both counting of layers and as the core gets deeper and deeper, more subtle methods for counting layers have to be used. And under a lot of weight, annual resolution is no longer possible. The time resolution is worse than a year. But at the top of the core, annual and seasonal resolution is possible. As you go deeper and deeper, a mile deep, for example, the ice is compressed enough under its own weight that the vertical age and distance resolution is lost, and some of the time resolution is lost. Okay, so what's shown here is the carbon dioxide amount extracted from dated ice cores. The extraction can be done in a vacuum chamber where the ice is either crushed or melted, even though CO2 is somewhat soluble. You can get about the same answer. And as a function of time, starting with time t equals 0 being now, or just before the Industrial Revolution, going back 50,000 years, 100,000 years, 200,000 years, 300, 400, the record actually goes back several 100,000 years more now, but this was the first version of the data. The actual amounts of carbon dioxide extracted from the ice core, representing the carbon dioxide that was in the air at the time that the ice formed. So this is a direct record of historical amounts of carbon dioxide, show that in the previous ice age, about 20,000 years ago, where I showed you a couple of quick clips, carbon dioxide amounts were 180 parts per million. And this number is about the same both in Greenland and Antarctica. In the interglacial warm period, such as what we're in now, the carbon dioxide amounts were about 270, call it 280 parts per million. Previous ice age, cold, 180 parts per million. Previous interglacial warm period, 280, 180, 280, 180, 280, 180, 280. The last 4, 5, 6 global ice ages have shown us that the natural range of carbon dioxide amounts was 180 to 280 parts per million, established by direct measurements. Have I said the word model? No. These are direct measurements. For methane, now the blue curve is temperature deduced from oxygen isotopes and some deuterium to hydrogen isotopes. The blue curve shows a proxy for temperature on this scale of about 5 degrees centigrade lower than the intervening warm period. So when it was cold, 4 or 5 degrees centigrade colder, carbon dioxide was lower. When it was warm, carbon dioxide higher, and so forth. Now with methane, another important greenhouse gas, same story. The natural range, when it was cold, 1/3 of a part per million of methane. When it was warm, 2/3 of a part per million. Cold, 1/3, warm, 2/3. Cold, roughly 1/3, warm, 2/3. Now, this is extremely important information because it establishes something about natural ranges. These measurements have been repeated, analyzed in many forms. And of course, it's important to know what leads and what lags. Did the temperature lead the carbon dioxide change, or did the temperature follow the carbon dioxide change? In roughly 2/3 of the cases, temperature led the carbon dioxide increase. In approximately 1/3, carbon dioxide led. So the current understanding is that the triggering event was the Earth's orbital parameters changing with the Milankovitch-type cycles, which changes the incidence of solar energy hitting the polar region, allowing, for example, more or less freezing, and then subsequent feedback forcing from carbon dioxide and methane. And by the way, nitrous oxide follows the same pattern. So, there is all kinds of evidence that the carbon dioxide increase that we're seeing now is from human activities. I'll mention a few strains of that evidence just real quickly. In my view, there's no real silver bullet here that says, oh, that's what convinces me that the carbon dioxide rise that we're seeing now is from fossil fuels. But there's 5, 6, 7 different lines of evidence. And I've said here that the carbon dioxide is approximately 85% from fossil fuel usage, that is the increase, and approximately 15% from deforestation and breakdown of exposed organic matter in soils. The evidence is certainly the amounts of, just from the lowest level up, the amounts of carbon dioxide increase are approximately the same as the fossil fuel release, within a factor of 2. The geographical patterns, the seasonal patterns, the isotopic contents of C13 to C12, if you take into account the atmospheric bomb testing and try to work around that, the carbon-14 contents of CO2 in the old days also made it look like this was a fossil fuel increase, and a few other patterns. But there's very little doubt that this carbon dioxide increase is due to human activities. Okay, what does it all mean on this energy balance scale now? I already said that this impact on the Earth's energy budget, which I think Suki Manabe may have been the first person to use the term radiative forcing, I'm not sure. We have to talk about that sometimes, because I'm trying to find this out. The carbon dioxide increase measured in the last few decades is giving rise to an extra about 1.6 watts per square meter of energy being trapped near the Earth's surface. The methane increase about 0.5 watt, nitrous oxide about 0.2, and a whole range of fluorine-containing chemicals that are not all chlorofluorocarbons. There's some hydrofluorocarbons, sulfur hexafluoride, and a few other exotic things like carbon tetrafluoride and perfluoroethane, not all of which is anthropogenic. Some of it may actually be natural, although I can't understand it myself. What I'm not showing on this graph is some complication of the other things that are changing the Earth's energy budget, namely aerosol particles floating around in the atmosphere, which are more difficult to measure, more difficult to quantify, but they may have a significant entry on this kind of a chart of maybe approximately -1 watt. So the net forcing that humans are applying on the climate system is of order 1.5 or 2 watts per square meter if we take into account the negative forcing due to, for example, sulfur pollution in the atmosphere leading to highly reflecting sulfate particles, especially downwind of industrial regions. But aside from that complication, I think the most important message here is the greenhouse gases. Okay, I said we'd talk about what's actually happening. There are 3 or 4 places around the world now where people are keeping track of temperature data very carefully. It's a very messy job. One of them is nearby here at the NASA Center in New York City, and they update this curve frequently. This graph, first of all, 0 does not mean 0 degrees on any scale. It's a reference point. 0 in this graph is the average of all temperatures measured on Earth between the year 1950 and 1980. People in this business often use 30-year reference periods against which to compare. Every one of these black dots represents an annual average of temperatures measured over land and sea, with progressively more precision as the record gets, as the observations get better and more numerous. There's probably 300 million data points in a graph like this. So what you see is that compared to the 1951 to 80 30-year average, the average temperature of the Earth was lower back in the late 1900s, there was a bit of a rise, although you can see that the noise level is pretty large here, and it's not clear that we had actually broken out of the noise completely until maybe 1930 or 40. And then whatever kind of warming there was reversed till about 1975. And this cooling, if it was a cooling, was most pronounced in the northern industrial latitudes, which is consistent with the use of high sulfur coal, leading to sulfate light-reflecting particles, especially downwind of northern mid-latitudes. That's not the only explanation, but it's one. But the most pronounced feature of this graph is the run-up since the late 1970s, 1978 or 80, where clearly we've broken out of any noise pattern. You need multiple years of data to get a good signal, so seeing a 30-year record like this is much more convincing than seeing a 2 or 3 or 5-year record, where successive years tend to be higher than the previous ones, but not always. I'll have a little bit more to say about this as we go along. Now, you can go into these data in much more detail because the average temperature of the planet is not really what we want to know. We don't base much of our civilization on the average temperature of the planet. So people are trying to go into much more detail. So here's the first cut of a breakdown. Southern hemisphere versus northern hemisphere. The same temperature data, again, from Hansen's group, but you get essentially the same numbers from the UK effort or the US NOAA effort, and then a recent entry into this work from Rich Muller. The southern hemisphere is lagging the northern hemisphere, and you see, for example, that when the northern hemisphere was relatively cold by recent standards in 2008 and 2009, you may remember the winners of those 2 years here were real winners like we haven't had since the 70s or so in North America, although Montreal set all-time records for 2 months in a row, 5 degrees centigrade higher than normal. Otherwise, we had a little bit of a cool northern hemisphere compared to recent years, although nowhere near like what it was in the 70s. But at the same time, the southern hemisphere set an all-time record high, 2009. In 2010, when the northern hemisphere was back up to something near the highest point, the southern hemisphere was down a little bit from its 2009 level. And when you look at regions, for example, here's a two-dimensional map showing the annual mean surface temperature as a function of geography on this false color scale. So you see that the largest warmings observed in this record have been in the high Arctic, and that's no surprise because you're aware of the excess melting going on, the loss of Arctic sea ice, the heaving of permafrost and so forth, which we've all seen in numerous ways. Over the oceans, there's much less warming. No surprise, because the waters have very high heat capacity. The marine areas are warming up more slowly. The land areas more quickly. In fact, they're warming up quite a bit more quickly. And this particular graph shows the patterns observed in 2010, 2005, and 1998, which were the 3 warmest years of the 130-year record, and then a month-by-month record. So getting down to geographical areas, you begin to see a lot more noise, a lot less monotonic behavior. There's patchiness all over the place, but when you average over significantly large chunks of geography and significantly long periods of time, you see a more or less monotonic record. And I think the people who are doing climate modeling have similar challenges. Well, now what about waters? The temperatures of the Earth's oceans are not measured as densely as the atmospheric measurements are. This particular graph is called heat content. It's from a group at NOAA, not here at GFDL, but a sister laboratory, which shows the heat content of the upper few hundred meters of the oceans worldwide as deduced from all the measurements available over about a 50-year period against some baseline. Although the data are noisy, the best fit is that the upper oceans down to the thermocline are warming up more slowly than the atmosphere, and the heat content, if you work out the numbers, this 4 times 10 to the 21 joules per year turns out to be about 10% of the extra radiative forcing, which doesn't surprise you too much. A lot of the excess heat being trapped at the Earth's surface due to the extra greenhouse effect is flowing into the world's oceans. However, this trend is not measured that well. There have been a couple of other recent analyses that come up with slightly different numbers because the ups and downs of individual years are affecting the trend line fit, of course. But the evidence is warming ocean surface water is down to about 600 or 700 meters, which is the part of the ocean that is in recent contact with the warming atmosphere. Sea level. Until about 1990, sea level was being measured around the world very carefully, but with very primitive methods. And this is a compilation of the best sea level measurements and then average globally. But in fact, what would happen with these primitive measurements, basically sextants and poles being pounded into the earth near seashores, is that there would be different sea level determined around the different continental margins under geological forces, wind conditions, currents, and of course measurement imprecision. But nonetheless, if you take all the measurements done in this careful but primitive way, they showed a rise of sea level in 100 years of about 16 centimeters, maybe 17. So that would be 1.6 millimeters per year. Now, the red part of this curve is something different. It's the modern era of sea level measurements done by remote sensing, done by ranging devices on Earth-orbiting satellites, some French instruments and some US instruments. And the up-to-date curve, and you can get an update virtually every few months from this site at the University of Colorado, shows a much better record in the sense of more accuracy, more sampling, a more representative average over all the ocean basins, and more precision. And the measurement shows a rate of sea level rise just about double what I had said earlier. So while it looks on this slide that the two records connect, when the first record came out, people thought, gee, that's good. And then when this higher rate of sea level rise was first observed, I think all of us said, well, it's not clear that this is really a doubling of the rate of sea level rise or even a significant acceleration. Maybe this trend is just measured better. But I think now we have good reason to believe that the rate of sea level rise is increasing. And that's because of some new measurements of ice on Greenland and Antarctica. This record came out around 2007. It was from a set of instruments which, personally, I never thought would be able to do this. It's from a set of satellites that orbit the Earth and measure the Earth's gravitational field and departures from a perfectly spherical Earth. The geodesy community has been doing these things for years. So, for example, when it's a pair of satellites that follow each other, and their position is linked to each other by K-band interferometry ranging in between them, and then their positions are in turn figured out by the whole global positioning system through the 20-some satellites. So they can track each other and the gravitational acceleration that each of them feels, orbit by orbit by orbit. So if the first one goes over a mountain range, it feels the extra gravitational attraction. There's a little bit of an acceleration as it passes over the mountains. The tailing satellite can pick it up, sees the same acceleration, but after a period of time, if something changes below, like, for example, a significant amount of snow deposited on the mountains, that can be measured. These satellites have now actually seen the seasonal changes in aquifer contents on the Indian subcontinent. But these were the first measurements of the showing that the total mass of ice in Greenland was decreasing. And when we saw this, I think a lot of us didn't know what to think, and I think many of us thought, well, this is just a 3-year record. In the climate business, 3 years really isn't that impressive. So this is an extension of the data now through 2010, and the best fit to the data is no longer a straight line, it's an acceleration. And the acceleration is 17 billion tons of ice per year, and the mean rate of ice loss from Greenland alone over this 8-year period is equivalent to 0.7 millimeters per year sea level rise. when the record started, this original rate was about 0.4, but averaged over the 8-year period now it's 0.7. And for Antarctica, this is what the gray satellite data show. Again, the best fit is an accelerating ice mass loss. The acceleration just happens to be about the same number. I haven't put the error bar here, 17 gigatons per year, but with a lower 8-year average contribution to sea level rise. The sea level rise that I mentioned earlier from tide gauge measurements of 1.6 millimeters per year, just 6 or 7 years ago, people couldn't get the budget to add up. Where does that come from? How much of the 1.6 is due to sea level, to seawater expansion due to the warming? How much of it is due to continental glacial loss? How much of it is due to Greenland and Antarctica? The numbers didn't add up. Now we know that the number is twice as big and the numbers do add up. You can now come very close to this 3.2 or 3.3 millimeters per year by adding up these two numbers of Antarctica and Greenland plus thermal expansion of the surface waters plus the loss of continental glaciers. So things are starting to be consistent as the data set gets longer and frankly as the signal emerges. These accelerations are causing bigger signals to be visible. I want to say a word now about whether we understand what's going on. Is there an explanation, and is it the only explanation? Well, I do want to mention one representative set of calculations from one of the stronger climate modeling groups in the UK that tries to solve equations from first principles. And the equations, as many of you here from Princeton and GFBL know, essentially go back to conservation of mass, fluid flows, conservation of momentum and angular momentum, and even try to keep track of phase changes in this rotating three-dimensional Earth. But there are, of course, approximations, but they do try to do as much as they can from first principles. And this particular calculation 5 years ago was trying to simulate the observed temperature increases that I showed you earlier, global average temperature, and you may be able to see this kind of spaghetti chart over it, trying to simulate that temperature increase, but without the human forcing, and you don't get the right answer. You get well outside of the range of noise. The observed is well outside what you've been predict otherwise. But when this particular group, and they were not the first to do it, but when they tried to include all the forcing, the greenhouse gases, a little bit of the aerosol reflectance, they get a global average temperature versus time, which is much more in agreement with the measurements. There's still departures, of course there are, and we can talk about some of those, but I think it leads me to say that physical principles do explain the warming since the late 1970s through the greenhouse effect. So, and you can do it quantitatively. Now the question is there some other explanation? And I said earlier that this 30-year air temperature and surface water temperature measurement showed something rather special in the last 30 years. What's different about this last 30 years is it's completely outside the range of all previous thermometer measurements. The rate of increase is greater than anything we've thought of, and it's also larger than any of the models can simulate with purely natural causes. And there's there's one other thing that's very distinctive about this last 30 years. It's the only time in human history when we've measured the output of the sun well enough to be able to say yes or no, is the sun causing these changes? Because it's been the favorite theory of many of us that what we're seeing may still be natural. But these are actual measurements now of what's called the total solar irradiance, that is the energy coming from the sun at Earth's orbit. These measurements are from Klaus Freilich in Switzerland and Judith Lean at the U.S. Navy Research Lab. And they've recently, Judith especially, is convinced that the absolute calibration is wrong by about 1/3%. The absolute calibration should be down here, but the relative measurements are pretty reliable. They've strung together several satellite instruments and come up with a 30-year record of total solar irradiance, showing that the 11-year cycle is a pretty good representative. The 11-year cycle that's been observed in other measures of the sun, like sunspot occurrence, the 10.7 centimeter flux index, and a few other measures of solar activity, that the 11-year cycle looks like a way to characterize the sun's behavior, that it's oscillatory, and it's very different from greenhouse forcing. This is not going to cause a warming trend over 30 years. It's an oscillatory behavior. By contrast, the greenhouse forcing is about 12 times larger. It's growing, and it's monotonically increasing. It's not oscillating. So I think what you conclude, based on these measurements, is the sun is not causing the recent climate changes. Okay. I've already mentioned the importance of the CO2 emissions. There's a group at Oak Ridge National Laboratory that does a very careful job of keeping track of all emissions of carbon dioxide from fossil fuel burning over like a 250-year period. But the most interesting part, of course, is the 20th century, as well as cement manufacturing, which contributes a couple of percent of the CO2. And, okay, what do you see there? Well, of course, the wars and great disasters like that influence things, but generally speaking, we're now emitting about 8.5 billion tons of carbon in the form of carbon dioxide into the atmosphere just from fossil fuel usage, whereas 100 years ago it was less than 1% of that number, and this number is rising quickly. These are some historical data on there's something interfering here, world marketed energy consumption over this 45-year period, where obviously previous to 2010, these are historical data, and beyond 2010, these are projections done by the U.S. Energy Information Agency, which is a semi-autonomous part of the Department of Energy. In the year 1970, the world marketed energy usage was about 205, 210. So on this scale, it would have been about here in the year 1970. So a doubling in about 30 years to about 415, and further projected increase like this. Well, the problem is that 80 or 85% of this energy is coming from the burning of fossil fuels with release of carbon dioxide, of course. Just to give you another picture of other things that are changing here. Whoops, something's happened here. Skype has stopped working. I apologize for Skype stopping. What I wanted to show just briefly is that the pattern of energy usage in the world is definitely changing much more towards developing countries, so that as we look to the future and try to come up with ways to, if we decide to manage carbon dioxide emissions somehow, that the challenge is now spreading from not just, for example, the United States, which had a share of nearly 25% of the CO2 emissions in 1990 and over 25% in earlier years, but shrinking. So as the world energy usage grows, the U.S. fraction is decreasing, and just as an example, the Chinese fraction of world energy consumption grows like this, and India more slowly. The EIA projections tend to be conservative. They don't recognize a lot of technology changes historically until they happen. But this is what's projected. Just to give you one other measure of how much momentum there is behind these changes. Coal consumption. And of course, you have to go into the end usage to understand the dynamics of all of this. But the Chinese consumption of coal has pretty much passed the rest of the world combined now and in the future. And as you know, there are many places of China that still don't have enough electricity to meet their own demands and needs. So the momentum behind these changes is going to continue. And something that Steve Pacala and Rob Sokolow have written on several times in the past decade is global carbon cycle. I have a cartoon here, obviously, from a Japanese colleague from several years ago, where we don't really know what a dangerous level is, I would submit, but the depiction here is obviously of a bathtub being filled with water, where the input is the anthropogenic emission due to fossil fuel usage, which I just said is over 8, but at the time he did this it was 7. Whereas the natural capacity of the bathtub to drain the CO2 or of the atmosphere to purge itself of CO2 is given by, it's about 3 billion tons of carbon in the form of carbon dioxide, about 2 billion tons a year going into the oceans, and about 1 billion ton going into the land. Now, these measurements are being worked on for decades now by people doing field measurements on CO2 exchange with soils and plants and oceanographic excursions, but also with atmospheric oxygen measurement by 5- and 6-digit precision in atmospheric oxygen measurements. You can convince yourself if you make very simple approximations that as carbon fuels are burnt, they consume atmospheric oxygen. If nothing else were going on, you would see the mirror image of CO2 rise with oxygen decrease. There are other things going on. There's oxygen exchange due to solubility with world's waters. There's oxygen being produced by photosynthesis. But when you take these data from Ralph Keeling, Dave Keeling's son, Michael Bender here at Princeton, and a few other groups, in my view, you get about the same numbers that the ecologists had already determined for these natural absorption rates. So what it leaves you with is that if we want to stabilize the water level in the bathtub, we have to either increase the ability of nature to take up the carbon dioxide or decrease the flow in. And of course, you can write down the differential equations and do this in a more sophisticated way if you want, but this is the bottom line. So it's these numbers that are the basis for people saying that if there were a desire to stabilize carbon dioxide amounts, it's not enough to stabilize emissions and have constant emissions, which intuitively you may think would do the job. It doesn't, because as long as the emissions exceed the drain down capacity, the carbon dioxide amounts will continue to grow. In fact, with these numbers, the carbon dioxide emission would have to be cut 2/3 to be able to stabilize the water level. So somewhere between 50 and 80%. And I haven't even added in the carbon dioxide being added by land use changes and deforestation. Well, where do we go in the future? The challenges are, how do we continue to improve our understanding of the system mechanistically and also try to make some kinds of predictions? The people in the field don't even use the word prediction anymore. They talk about projections because they realize how hard it is. But obviously, there's concern over global temperatures and their extremes. What will the statistics of future temperature patterns be? How many more extreme hot events will there be? And by the way, the record is showing from Jerry Meal at NCAR, in his published papers, that the frequency of new high temperatures compared to the frequency of new low temperatures, it's about a factor of 2 out of balance, maybe 2.5. So things are consistent, but obviously predicting temperatures and their patterns and their, especially on continents, what is the rate of sea level rise to be expected? This is very, very primitive science at this point, because the actual mechanism of not only ice melting in Antarctica and Greenland, but the delivery of heat from ocean currents and the actual mechanical problem of how the ice shelves are being eaten away and then allowing the stacked up ice behind it to flow downhill with no barrier in its way again to go into the ocean where they will float and then eventually melt. That's just now coming into view, and even the best mechanistic calculations, I don't think anybody would claim that they can make good predictions, especially because there are choke points where the action is happening as opposed to being spread out uniformly. There are a few places where the ice is being observed to accelerate, where the breaking is occurring, and the ice flows are happening, both in Greenland and Antarctica. One of the key variables that has to be most important is precipitation amounts and patterns. There is already some observations that the frequency of high-intensity rainfall events is increasing. This is to be predicted from first principles, from the model calculations. It's being observed in empirical records, but the very nature of precipitation, being a phase change, being what a soft matter physicist might call a catastrophic event, if you will, this is very hard to predict. But it's essential because so much of what we do to manage water for irrigation and agriculture and so forth is, if we can anticipate these changes and then deal with them through adaptation mechanisms, it will certainly be valuable. The frequencies of extreme events is, I would say, in its infancy of prediction. There are some awfully smart people working in climate modeling who are working on all of these. And of course, the management issues and the carbon cycle, many of which have been identified here on the Princeton campus, are real challenges for scientists. And because, as I said earlier, of the extreme closeness of the societal impacts, both economic and on human activities, because it's so closely connected to climate, this work has to be done well and quickly, and no matter what the answers are, they're going to be criticized by people with differing interests. It happens all the time. Francois Morel here led an academy study last year just to talk about what's known about ocean acidification and what needs to be known about marine biology based on the fact that the uptake by the oceans of carbon dioxide is already leading to a reduction in alkalinity in the oceans and will lead to more acidification. Although there are some complications, generally speaking, you can pretty well predict a decreasing pH just simply due to the absorption of carbon dioxide. So, funny, the scientific community didn't speak up early enough that we've been saying for a long time, well, the absorption of carbon dioxide by oceans is a good thing because it's preventing the atmospheric concentration from going up so fast. In fact, there's no free lunch here. And we simply don't know yet what the sensitivity of ocean biota are to these geologically rapid changes in ocean pH, as well as other things in the oceans. I'll stop with one final observation. 20 years ago, next year, there was the creation of the United Nations Framework Convention on Climate Change, which President Bush 41 signed as the most natural leaders. And one of the important provisions there said that the objective of this conference and all the machinery they set up through this UN FCCC, the Framework Convention on Climate Change, was aimed at preventing dangerous human interference with the climate system. But they didn't define what dangerous means. So the question is, who should define dangerous? And should this be a role for the scientific community also? Or is this a decision that should be based completely by a broader spectrum of the public? I went off some time ago saying that it has to be defined, especially in a representative democracy, by the people represented who represent us. But in many, many public talks, I dug up these slides. I haven't used them in several years, this last two. I did it because I've been told by many public groups, no, this is a job for the scientists. Why don't you tell us what's dangerous? Well, I don't know what you think, but I don't think the scientific community has quite agreed yet. So I will stop here, and as I said, I tried to cover this material in my own way, and probably each one of you would have presented these things very differently. So thank you for your time.
So we're just going to take some questions, so have at it.
Anybody? Yes.
Temperature rises, carbon dioxide rises, and other fact, 2/3 of the time. So you tell you the reason for that? Only one percent of the time, carbon dioxide is
That's how it seems to have worked in geological history. Now we superimpose on that a human increase of CO2. He's asking me if the fact that in geological history, the record that we have, the fact that it shows that CO2 increases lag the temperature increase perhaps 2/3 of the time, if that doesn't undercut the rest of what I'm saying, essentially. And I say no. The record shows, if it can be believed, that yes, CO2 did lag the temperature increases in the past, but now we know that we're adding the carbon dioxide beyond the previous ranges, and we know what the radiative effects are from laboratory spectroscopy and easy calculations. I think we have to go where the science shows us. I don't think there's anything logically inconsistent there at all. Kind of like listening to music in a room. This is really wild, but if you had maybe symphonic music playing in a room, and then there was another speaker playing rock and roll at the same time, both things are happening, and you can actually hear them both happening, and it's just a question of which one has the highest volume. So I think both of these things are happening. There are natural changes going on all the time, but the dimensions of this human forcing are getting large. Yes, you were there.
I'm going to refer to the same geological time. The ice core samples it's very striking, the connection, the correlation, the correlation between the carbon and the temperature rise. What worries me is one thing. In a given core sample, it looks like you're looking at a given point in the region. But as you go down, it could be that in fact the ice has been moving, and we're talking about actual different regions. Can you comment on whether this makes any difference? So we're not really talking about a given point on the Earth.
That's right.
We're actually talking about what looks like a given point now is actually different places.
First of all, if you really want a solid answer, talk to Michael Bender here on campus, because he does some of this work. My understanding of it is these locations where the ice cores are being extracted are chosen very carefully for any evidence of previous melting or fractures in the ice. You can see where shear would have happened with lateral movement. They select these cores very carefully to try to find ideal conditions. In the recent cores, which are actually, you can get time resolution in the last 200 years, they're being done in areas of very rapid accumulation of snow so that you can still get resolution. And then finally, the fact that these point measurements, as you call them, agree between Greenland and Antarctica tells you that you can't be too far off. But as a matter of fact, I don't know how many cores are rejected by the criteria I mentioned, and that's where Michael Bender appeared. Michael had to leave earlier, but he knows exactly how these cores are selected and what criteria are used to reject cores that show any evidence of lateral movement or melting.
In examining extreme weather events and more huge fluctuations, does it make sense to think of the atmosphere thermodynamically as an engine, or perhaps an ensemble of engines, and as you put more heat into the warmer reservoir of the engine does what it does more intensely? Does that make any sense?
Yes. And I am not a fluid dynamicist, but we have the geophysical fluid dynamics laboratory just off the Princeton campus, where there are people who have thought about that all their lives. And generally what you see is transport towards the poles, and you can try to figure out then what happens in a perturbed climate. Yes. We also know that we have things like the Clausius-Clapeyron relation of the vapor pressure of a liquid, and what happens with temperature. More moisture is being forced into the air. Now that doesn't mean that the patterns of water vapor in the air are going to stay the same. But someone who says that the atmosphere is going to dry out as the world gets warmer seems to me has a big burden of proof on his or her shoulders to say that it's going to happen. Because the tendency of a liquid to evaporate with temperature is, as you know, a strong function of temperature. There are people who are saying that the upper atmosphere is going to dry out as the Earth gets warmer. The data say that they're wrong, and the principles say that they're wrong, but they keep saying, yes.
My question has to do with the graph you showed where there was a regular pattern, I think, of 180 parts per million, and then at 300 some parts per million, et cetera, and it went up and down, up and down. Now we're progressing upward, if I understand that chart. My question is, if you're at the trough end, what would be the effect? Would it counteract, if we go back to that trough point, or will we go back to that trough point, would it counteract the rise?
There's some lag times built into the system that, for example, if there would be no further rise in carbon dioxide, we expect about another ½ degree warming in the next several decades with no further changes at all, just due to lag times in the system. So you couldn't achieve anything overnight. But the only way we can answer that question, in my view, is to go through these numbers that I call radiative forcing, that is, the changes to the Earth's energy balance. I don't know of any other way of understanding it.
When you show the dramatic increased concentration of CO2 in the last 40 years, the implement was the people with depression that also temperature will rise more or less proportional to concentration. However, you didn't mention anything about saturation of optical depths of the CO2, which increasing from, for example, 400 particles per million to 800 doesn't increase temperature very much because CO2 has very narrow bonds, very high intense absorption band, but quite narrow, and therefore saturate quite quickly. Could you comment about this?
Yes, I disagree with one word that you said. You said temperature wouldn't change very much. I think that's a subjective judgment. It will not change proportionally because of what you said. The absorption features in CO2, the 15 micron band, the 10 micron band, are, generally speaking, the radiative trapping is roughly proportional to the logarithm of CO2 now. It's a slow curve of growth because of saturation. But in the hot bands and in the isotopic bands, there's no saturation. And these are such huge amounts of CO2 that even a logarithmic increase is pretty significant. Methane is in roughly a square root curve of growth domain, and the fluorinated chemicals and nitrous oxide are pretty much linear.
In such case, also water vapor starts to play more and more important role.
Oh yeah.
And that moment, when the water vapor, with saturation is much lower, the overall CO2 effect, the saturated and water vapors will not have so-called positive feedback and negative feedback, as we mentioned earlier, so it's negative feedback. So this
complicated business
has to be considered as a balance.
It is, and I'm pleased to say that I think the best laboratory spectroscopy and radiative transfer techniques are in these computer codes, the simple ones and the complicated ones. There could be errors, but are the people in the business, do they know what they're doing? The answer is yes. Now, there are positive feedbacks, that is, that will amplify the original signal. There are negative ones. Part of, including in the carbon cycle, not just the atmospheric physics, that makes this is one of my other messages, a scientist perspective, is that while we're dealing with all these societal and political issues, there's also tremendous scientific challenges. The spectroscopy is pretty well known.
I think we should probably take one more question, and then we'll have a reception upstairs afterwards.
George?
You commented on the difficulty of prediction. Would you comment on whether there are schemes for geoengineering in which you think there might not be predictability?
I think Professor Whitesides is asking about whether there are any ways that humans could intervene by trying to engineer a stabilization mechanism and how predictable those methods might be. gather a few ideas, but there's very, very little refereed literature. The Russians came up with the first idea involving putting massive amounts of sulfur in the atmosphere to create both smoke and reflecting particles. Budiko, wonderful stuff, but it hasn't progressed much since then. So it is probably feasible to reflect as much sunlight as necessary to counterbalance the greenhouse gas forcing on an energy basis. But I would say it's not possible right now to predict what other things would happen, including ocean acidification.
Yeah.
But I think it's an area for research, George, that really ought to be looked at, but with no commitment to actually try any of these things. I think we need something like a moratorium that the molecular biologists placed on themselves back in the 70s to not allow a particular class of experiments until all kinds of safeguards were in place. So on geoengineering, I think we should be doing paper research, but not much in the field yet.
Well, I think we should thank Ralph for saying you should have to short that around. A framed copy of the announcement that we've had all over the place. The twin of this thing will hang in Guyot Hall, and given Princeton's traditions, will approximately be here for a millennium or so.